Hello students, welcome to this lecture in which we're going to talk about surface area. And even though you've done some surface areas in Calculus 2, but let's approach it from Calculus 3 point of view. So we're going to consider a surface. Let's call it sigma. And the form is z equals to f of xy. Our standard way. And it's going to be defined over a region, R in xy plane. So basically what we have something like this. So we have 3D space, and here we have some kind of a surface. And on the bottom we have the region R. So this is our region R, and so over here we'll have the same region. All right, that's our idea. And then if we draw the region in xy plane, if we take our region R and we draw it over here, then it looks something like this. Maybe a little bit bigger picture. So we have, so this is our region R. And what we can do, we can take this region and we can draw the horizontal and vertical lines, maybe of a different color. So what we can do, we can split our region into the rectangular pieces, like this. All right, so basically if we think about this region, inside as R sub k, and this region over here has delta x sub k over here, and delta y sub k over here. All right, so we have to assume a couple of things. We will assume that partials are continuous, that f has continuous first partial derivatives, at the interior of R, points of R. So basically we have so the tangent planes are non-vertical. That means tangent planes are non-vertical. That's all it means, that partials are continuous. So we subdivided the region into smaller rectangular regions, and we can label them from R1 to Rn. Subdivide R into rectangular regions. R sub 1, R sub 2, R sub n. So let x sub k, y sub k be the lower left corner of the case rectangle R sub k. So basically, if we go to our picture, this point over here is exactly, this point here is x sub k, y sub k. That's what we mean by the lower left corner. Okay, and let a sub k be the area of R sub k. Then I said let me say it's delta a sub k, delta f sub k, where, let me rephrase it, where delta f a sub k is equal to delta x times delta y, because if we take this distance delta x over here and this distance delta y over here and multiply it, we're going to get this little rectangle. All right. So basically, then, if we take this area and think of it, what would it be on the surface? What would it be on the surface? So basically, if we have a surface, all right, and we have area R sub k over here on the bottom, so this is x, y, and z. So if we take area on the bottom R sub k over here, little rectangle, and here on the surface we'll have something like this. Some little piece of a surface, let's call it sigma sub k. Let's call it sigma sub k. And this corner over here, the lower left corner from the picture, that was x sub k, y sub k. This will be this point over here, which is, let's call it p sub k. So if we zoom in on this piece, this piece looks something like that. So this is our sigma sub k. This is our sigma sub k. So what happened over here, we can construct a tangent plane. We'll construct a tangent plane. So this is our tangent plane, starting at p sub k and having two vectors going in this direction. So let's call it q sub k and r sub k, for example. So what would be the corner p sub k? The corner p sub k will be given by corner p sub k. So on the xy plane, it's just going to be given by x sub k, y sub k. But for the z value, we have to take f and evaluate it at x sub k, y sub k, and this is how we get this corner point p sub k, this point over here. All right. So let's denote this area of this blue patch. Let's denote this area of the blue patch as delta S sub k. So let this blue patch over here will be delta S sub k. So we can approximate the area delta S sub k by the area tau sub k, which is the area of the tangent plane. All right, so T sub k is the area of the tangent plane. I say T sub k, tau sub k. So this one over here is tau sub k. All right, so in order to approximate this, we need to find these vectors q sub k and r sub k. So first, q sub k will be given by, in this direction it's the same as this direction over here, so just delta x sub k. In the y direction it doesn't really change, so it's 0 in y direction, and in the z direction it's a partial of z with respect to x times delta x sub k. All right, so this time that, so we're going to get this vector over here. Also, we can get r sub k by the same reasoning, by taking 0 delta y sub k and partial of z with respect to y times delta y sub k. All right, and so then we know that tau sub k is the area of this is a parallelogram, right? This is a parallelogram, and the area of the parallelogram is the cross product of q and r. So we have to calculate q sub k cross r sub k to get the area, and this will be approximately delta S sub k, approximately. When our change is small, when delta x sub k and delta y sub k are close to 0. So small step to the right. So let's compute this cross product. So we need to compute this cross product of q sub k and r sub k. So let's do that. So we're gonna get so let's do that. So q sub k cross r sub k is equal to I, j, and k. So we have delta x sub k 0, then partial of z with respect to x, delta x sub k, and for y it's very similar. So partial of z with respect to y times delta y sub k. So if we calculate it for the I, we're going to get the products of for the I, we're going to get 0. So it's going to be negative dz dx times delta x sub k times delta y sub ki. Then we have negative for the j, so it's dz dy, this part, times delta x sub k, delta y sub k, j, and sorry, here it's should be minus, plus, then for k we have just the product of delta x sub k and delta y sub k. Alright, so we calculated everything. We see that delta x sub k, delta y sub k is a common factor. So we have negative partial of z with respect to x, I minus partial of z with respect to y, j, plus k times delta x sub k, delta y sub k. So that was, this was just the cross product, not the length of the cross product. So we can say delta s sub k is approximately the length of this vector, Okay, so we have to calculate the length of this vector. So it's going to be the square root of so this is a fixed number, this is a fixed number, so we can take it and put it outside, since they will be the same, these are just constants. And then we have to find the magnitude of this vector over here. So this is going to be d partial of z with respect to x squared, partial of z with respect to y squared, and 1 squared is 1. So this is approximately delta s sub k. So to get the s, we have to add up all of these little s sub k's. So we're going to have a sum when k goes from 1 through n. We have a square root of partial of z, partial of x squared, plus partial of z, partial of y squared, plus 1. And this is basically delta a sub k, right? It's the area of little piece on the bottom. Then we just need to take a limit when n goes to infinity. So we say s equals to the limit when delta x goes to 0, Basically, when n goes to infinity, it's the same thing. N goes to infinity. Of the sum when k goes from 1 through n of the square root of partial of z with respect to x squared plus partial of z with respect to y squared plus 1 delta, sorry. Next step is dA, but now it's delta A sub k. And we know this limit is by definition the double integral over the rectangular region of this function when we have dA at the end, and here we have dz dx squared plus dz dy squared plus here, sorry, so plus dz dy squared plus 1. And that's our formula, right? This is our formula that we're going to use for the surface area. Alright, so let's do this. Let's do an example. And in this example, we're going to calculate the surface area. Find the surface area of that portion of the curve. I said curve, it's wrong, it's surface of the surface z equals square root of 4 minus x squared that lies above the rectangle R in the xy plane such that 0 is less or equal than x is less or equal than 1, and 0 is less or equal than y is less or equal than 4. Alright, so we have a rectangle for x between 0 and 1. So on the x-axis it goes up to 1, on the y-axis it goes up to 4, and we have this region over here, and on top we have the surface such that z squared, if we square both sides, if we take z equals to 4 minus x squared, and we will have z squared equals to 4 minus x squared, so it's x squared plus z squared is equal to 4. Alright, so our surface on the top will be something like this. Alright, so that's our surface S over here, and we would like to find its area. Right, so, and this is a part of the cylinder. This is a part of a cylinder. This is a part of the cylinder, right? So let's try to build our S. Our S is integral over the rectangular region of dz dx squared plus dz dy squared plus 1, and we have a square root, and we have dA. So we say it's equal to the integral over the region, and we have a square root. So let's calculate dz dx for this function. So it's going to be so our function is square root of 4 minus x squared. So it's going to be 1 over 2 square root of 4 minus x squared times 2x. So we'll put 2x over here, and it has to be squared. Then the partial with respect to y will be 0, so plus 0 squared plus 1. And we have dA at the end. So we move forward, so we have an integral, and on the y-axis we go from 0 to 4, so it's 0 to 4. On the x-axis we move from 0 to 1. We have a square root, so 2 goes away, 2 goes away, and we have, and obviously has to be negative, I forgot the minus, negative 2x, right? So if we square the expression, all right, so if we square the expression, what do we get? We get x squared over 4 minus x squared plus 1 dx dy. So 0 to 4, 0 to 1, and we add up, so we're going to get x squared plus 4 plus, minus x squared, if we create common denominator, divided by 4 minus x squared dx dy. So we're adding in this 1. So x squared and x squared goes away. Okay, and all right, I was looking at it, and I understood that I didn't really do it right, so let me redo it a little bit over here. I don't think I simplified well. So what do we get? We get integral from 0 to 4, integral from 0 to 1. So we have x squared. Yeah, I think I did it right. So let me do it one more time. So x squared plus 4 minus x squared over 4 minus x squared. I think I did it right. Alright, so what do we get in this case? And dx dy. Alright, so basically what do we get? I'd like to finish this problem off because of the technical issues couldn't work. So we have a square root of this expression, And finally we have integral from 0 to 4, integral from 0 to 1. We have 2 on the top, square root of 4, square root of 4 minus x squared dx dy. So 2 is a constant, so we can put it up front. Then integral from 0 to 4. And for this one, we can think of 4 as 2 squared minus x squared. We can think of this expression. And 1 over the square root of a squared minus x squared. That's an arc sine, the rule for arc sine from calculus 2. So we'll get arc sine of x over 2 dy, and this is evaluated from 0 to 1. So if we plug in 1, then arc sine of 1/2 is pi over 6. If we plug in 0 for arc sine, we're going to get 0. So it's going to be 2 integral from 0 to 4 of pi over 6 dy. So it's 2 times pi over 6 times y, evaluated from 0 to 4. So 2 and 6 we can divide, and so we're going to get 4 pi over 3 minus 0, right? So 4 pi over 3, that's our area of that surface. So another example that we're going to do is the following example. So in this example, we have to find the surface area, find the surface area of the portion of z equals to x squared plus y squared below the plane z equals to 1. Z equals to 1. Alright, so this function is a paraboloid. Basically, it's no matter how you cut it, you're going to get a parabola. So we plotted it before with a wx maxima, so in any direction we have a parabola. We have a parabola, and z equals 1, it's a plane that goes through through 1. So over here we're going to get a circle, and this surface over here is z equals to x squared plus y squared. And this plane over here is z equals to 1. So basically, if we project this onto xy plane, if we project it onto xy plane, we're going to get a circle on the bottom. We're going to get a circle on the bottom. And this circle is going to be x squared plus y squared is equal to 1, because if you take z equals 1, that's how the circle looks on top, so if we can project it on the bottom. So as you can see, our region on the bottom is a circle. Alright, so according to the rule that we derived before, is surface area is double integral over the region of the square root, and here we put the partial derivatives of x squared, which is 2x squared, plus the partial derivative with respect to y, which is 2y squared. We have plus 1, and we have dA. So if we simplify this expression, what do we get? We get 5 4x squared plus 4y squared plus 1 dA. And since we can factor 4 out, that's going to be square root of 4x squared plus y squared plus 1 dA. And x squared plus y squared, it's easy to think of it as in polar coordinates, right? So we can use polar coordinates, right? We can say x is r cosine of theta. We can say y is r sine of theta. Unfortunately, dA doesn't transfer directly. It has to be r dr d theta, right? So we have to introduce this r because we discussed it in the previous lecture, right? We also need polar limits of integration. So let's try to do that. We'll say that S is equal to integral. So for the angle, it's clear. We can go from x-axis, from the positive x-axis, all the way around, and so that's going to be 0 to 2 pi. And for the radius, we have to go from the inside all the way to the outside of a circle, so from 0 up to 1. So 0 to 1. So we have a square root. Then we put r cosine for the for the x and r sine for the y. So it's going to be 4 r squared cosine squared plus r squared sine squared plus 1. I forgot the angle, theta and theta. So, and we have dr d theta. So if we do this out, then we factor out r squared, so we're going to get 1 for cosine squared plus sine squared. And our formula becomes 4r squared plus 1. And here I forgot, sorry, it should be r here too, because it has to be this r. So it's going to be r dr d theta. All right. So we can use the substitution for the this square root. So we can say that if we want to calculate the integral from 0 to 1 of square root of 4r squared plus 1r dr, then we'll take a u to be 4r squared plus 1. Differential of u will be 8r dr, because derivative of this will give us 8r. So dr will be du over 8r. So we have an integral u to the 1/2, then r, then dr is du over 8r. So r and r goes away. If we take 0 and plug it in over here, 0 plus 1 will be 1. If we plug in 1, we're going to get 5, because 1 squared is 1, 4 plus 1 is 5. So we calculate, so we're going to get u to the 3/2 over 3/2, which is 2/3, evaluated from 1 through 5. All right. So we plug everything in, we get 2/3 5 to the 3/2 minus 2/3 and 1 to the 3/2 is 1. So that's our expression for the inside. So that means we go back over here, we say the integral from 0 to 2 pi of this expression over here. So we have 2/3 5 to the 3/2 minus 2/3 d theta. And finally we have Finally, we have 2/3 5 to the 3/2 minus 2/3 times theta evaluated from 0 to 2 pi. So finally we have 2/3 5 to the 3/2 minus 2/3 times 2 pi. Because when we plug in 0, it's going to be 0. So this would be our answer. And this concludes this lecture, and I'll see you in the next one.